So welcome to this session about supergravity at this conference. And just a few words of introduction about the talk we will have here today. So in this session, the speakers will cover a range of different topics revolving around supergravity. So we will start with the talk by Alice Luscher, discussing very recent advances in the application of localization techniques in the context of supergravity. Then there will be two talks, one by Alexia Nix, who will discuss some exact quantum field theory computation with the gravity dual, in particular regarding some Wilson loop calculations. And then Vasil Dimitrov will report on some very recent, I believe, unpublished progress. Where is Vasco? There. Extending the successful microset counting of BPS ADS5 black holes to the realm of non-supersymmetric and thermal black holes. And finally, Tancredis Schettini-Gherardini will discuss some new developments in the classic topic of Kaluza-Klein theory with some applications also in differential geometry. So I believe these are all very interesting topics, all different from each other, and will be a good representation of how interesting it is to do research in supergravity. So let's start with the first talk by Alice Luscher, who will talk about equivariant localization in supergravity.
Thank you. So, yeah, thanks to the organizer for giving me the opportunity to talk today. So, as Dario mentioned, I'm going to tell you about some recent progress, some recent work we've done with Pietro Benetti Giannolini, Jerome Gauntlet, his student, Yusheng Zhao, and my supervisor, James Sparks, on applying equivariant localization methods in supergravity, and more particularly some results we got in 40-gauge supergravity. So a subtitle for this talk could have been how to compute supergravity observables without really trying. So what I mean by that is that we want to be computed some integrals over space-time or a subset of space-time. For example, here the free energy would be some Ricci scalar and some matter fields. It looks like in order to obtain the on-shell action, we would need to know an explicit supergravity solution, so a metric on our space-time, in order to perform the integral. And knowing this explicit solution requires to solve some supergravity equation of motions or some killing spinor equation. That's generically a difficult or at least tedious task that has to be done case by case for different model. And so the question we want to ask is whether there is a way to obtain these observables, perform these integrals, without having to solve any of these supergravity equations. And so the answer is yes. That's why I'm talking today. That relies on the use of equivariant localization methods. So we want to be computing these observables. There are integral of n forms over some n-dimensional space-time. And using some fixed point formula, equivariant localization theorems, we can recast such an integral to some contributions of lower degree forms on some lower dimensional subspaces. And that makes our work easier. In particular, we'd never need to know an explicit solution for our space-time. So in a minute, we'll make clear how these higher and lower degree forms are related, which kind of contributions we pick up. But what I want to highlight first is that we're never going to solve any equation. Our results only depend on the topology of our space. And as such, we can obtain results for families of theories that can look quite different. And if you were to actually compute them, you would need different methods and so on. But here we get these results out of one formula, basically. So that's really like easy to obtain all these classes of theories. So in the first part of this talk, I'm just going to tell you what equivariant localization is, make this fixed point formula statement precise. And then we're going to apply it in particular in 40-gauge supergravity with matter. And I'll end with a discussion. So the type of solution we want to consider, we just need that they have a symmetry. Could be any symmetry for the localization theorems. But here we're going to focus on U1 symmetries. And to this U1 action, we associate a killing vector that I'm going to denote by psi. Out of this killing vector, we can build an object called equivariant exterior derivative, which is just the usual exterior derivative to which we add a contraction with the killing vector. And so this object naturally acts on polyforms, which are forms composed of forms of different degrees. So because D would raise the degree of raise the degree of a form by 1, and the contraction lower the degree of the form by 1, so that acts on forms of different degrees. The type of polyforms we're particularly interested in are the ones which are called equivalently closed, which is if we act with this xi on them, we get 0. So if we look at that degree by degree, that means that we want our top form part to be closed in the usual sense of the term, and then that each degree cancels, so xi in the top form part should be d of the next degree, and so on up to xi in phi 2 should be d of the scalar part of our form. And if this series of equality is realized, then the full polyform is equivalently closed. So why are we interested in this type of polyforms? It's because we have this old math theorem from the 80s telling us that the integral of such an equivalently closed form localizes to some fixed point contributions. So we're starting with this m-dimensional integral, and as this phi is equivalently closed, it just reduces to a sum of contributions on some subspaces of this initial space of lower dimension. And what's special about these subspaces is that they are fixed under the action of the symmetry. So the killing vector vanishes on them, so hence named fixed points. And then what we are evaluating is just the lower degree forms that are in our polyform. So this F is just picking up the right degree of form inside of our polyform to be integrated in on these subspaces. And then the other ingredients that we need is to write our killing vector in terms of some weights on the normal space to these fixed subspaces. So if we had our total space, which would be this kind of sphere with a fixed point maybe at the pole, we can write our normal space at the pole, which is rotated by the action of the killing vector in terms of some line bundles, and the killing vector is acting with rotating each line bundle with a certain weight, which are these bi's that are appearing in the formula. And then we also have the first Chern class of these line bundles that compose the normal space to the fixed points. So that still looks a little bit abstract, so let me show you what it can look like a bit in practice. So what we want to do first is just to rewrite our denominator. We expand it in a power series, and this power series is naturally going to truncate at some orders. And so eventually, like if we were to just consider a two-dimensional integral, so the kind of fixed points we would have are just isolated fixed points. And so instead of having a full integral, we just pick up scalar contribution. So we're just evaluating the zero form part of our polyform at a point. And I'm going to show you an example of that just on the next slide. Then for the rest of this talk in supergravity, we would be more interested in looking at 4D integrals. So in that case, we could pick up contributions either from isolated fixed points, again, we're just evaluating a scalar at a point, or from fixed surfaces, in which case we could have contributions from the two form or zero form parts together with the first Chern class, so also adding the second term in our expansion. You could go higher order, but that's not going to be relevant for us today. So let's just see how that works with a very simple example. So we can use this fixed point formula to obtain just the volume of the two sphere. So in that case, the form we are integrating is just a volume form on the two sphere. So we take it as being the top form part of some equivalently closed form. So we want to complete this phi 2 with a lower form to make it equivalently closed. So our killing vector in that case is just the one rotating the sphere with a certain velocity parameter b, if you want. And so now we're contracting this psi into our top form part, and we directly see that it's like the differential of some zero form thing that we called phi 0, such that now the polyform composed by phi 2 and phi 0 is equivalently closed. And we can apply our fixed point formula that I was showing on the previous slide. So we just need to know what the weights are. So the weights are just directly this b parameter. So fixed points are the poles, sorry. And so at the two poles, we just have b as the weight with a change of sign because of the change of orientation on the sphere. And so you just pick up the phi 0 part evaluated at the two poles with the weights. You have 2 pi times 1 minus minus 1 we got 4 pi the expected volume of the 2-sphere. So here that's a trivial example, so we know the metric. So what we would be interested in doing is to apply these same ideas in supergravity. So in this case, typically the U1 action we would be considering is implied in our solution by some supersymmetry. So even without knowing the solution, we expect to have this U1 symmetry. The way we're going to build our equivalently closed form, we cannot just look at it as in the previous example and know that sine is the derivative of cos. So the way we're related, our fields are using some bilinears and killing spinor equations. I'm going to say it more precisely just in the next slide. But the point is that we can do that work only once to build like this equivalently closed form. Start with a top form part, complete them using these bilinears. And then the formula that we get, we can use this, we can just pick different topologies and get different type of fixed point sets and just get observables for various theories out of one set of equivalently closed form. So now that we are considering supersymmetric solutions, we have a killing spinor. It's following some killing spinor equation, typically of the form some differential plus some fields gives 0. And so out of this killing spinor and its conjugates, we build a set of bilinears, some scalar ones, some 1 forms, some 2 forms, and so on. And these bilinears are going to follow some constraints that are directly coming out of this killing spinor equation epsilon is following. And one of the constraints that they're following in particular is that the vector field that is dual to this 1 form is killing. And so that's the one we're going to be using to do equivalent localization. And an example of some constraints we could have could be schematically of this form. Differential of one of the bilinear could be the contraction of our killing vector into some field strength, some related to the gauge fields. And what we would deduce from that is that we can build an equivalently closed form which has for 2 form parts this field strength and then a 0 form part that is just this bilinear. And then we could use this equivalently closed form to be computing fluxes, for example, by just evaluating P on some fixed points. And more generally, what we're trying to do is just to pick a term form part that is something that's interesting to integrate over to get some observable, and then use similar constraints to find out what the lower parts should be. So let's see what it can look like for 40 gauge supergravity. So the model we're considering is just, so we have 40 gauge supergravity with some vector matters. So we have the usual Ricci scalar, and then we have some scalar fields in our vector multiplets. We have a kinetic term and some potential for them. And then we also have some gauge fields in our multiplet with some kinetic term and some theta angle. And what's particular about these models are that all of these functions appearing in the action, this G, V, I, R, they can all be specified by a single function of the scalar fields called the prepotential. And so if you give me a prepotential, you're specifying which model you're using for me. And the last thing is that we're looking at Euclidean theories, which can be straightforwardly obtained from the Lorentzian one by just taking the scalar field and its conjugates to be independent variables. So we're using the tilde rather than a bar. So now we want to use equivalent localization to obtain the on-shell action, so actually perform this integral. So we're going to take this thing to be the top form part of some equivalently closed form, or rather we first apply the trace of Einstein equation just to rewrite the action slightly differently, and then that's going to be our top form part. And so now we play our game, find some phi 2, phi 0. I'm going to flash you the expressions that we found, but not get into details in what's entering. They're just a bunch of definitions, but just to show you they exist. That looks something like that. So that's our top form. And then we have some lower form parts with our prepotential and some scalar fields entering, basically. So then this is just the localization formula on a 4-dimensional space I was showing you before. We can pick up contribution either from isolated fixed points or from fixed surfaces. Then we can just plug in the forms from the previous slides and evaluate. Generically, we would have some boundary terms as well, but it can be shown that for our models, their contribution just end up vanishing, so I'm not going to get into details of them. So if we go ahead and plug things in, do a little bit of work to evaluate them, that's the general formula we find for the free energy of the 40-gauge supergravity with arbitrary vector matter. So here we have our prepotential, this F, and then the U's are just some function of the scalar fields at the fixed points. So that's really just the like what they look like at the fixed points that's going to enter. The plus minus denote the chirality of the spinor at the fixed point. Can be shown that the spinor has a definite chirality on each fixed point set. And an interesting thing is that in this U plus and U minus, there are going to be only functions of either the scalar fields or their conjugates. I mean, that is not their conjugates anymore in Euclidean, but either the Z for U minus or the Z tilde for U plus. So you're only going to pick one type of them at each fixed point. And the P's are some magnetic fluxes associated to the gauge fields through the fixed surface. Here are still our first Chern class and our weights. And the beauty of this formula is that we never solved any equation to get it. Now we can go ahead, pick some superpotential, pick some topology, and we just directly obtain the free energy of our model. So that's what we're going to do on some examples now. So the free potential that we pick is the STU1. So just, we pick this one because then we can uplift to 11 dimension on S7, and so we have ABGM as a dual, so that's a nice field theory dual. And then picking different topology for our M4 is just putting ABGM on some different background. So that's something that is nice. And so I'm going to show you briefly like 3 examples where we can have contributions from each of these 3 terms that we have. So the first one is this Euclidean black holes called black saddles by these authors. And the topology is just some R2 times the Riemann surface. And our killing vector in that case is rotating the R2. And so it's fixed, the action is fixed at the origin, and what's fixed is the full Riemann surface. So we have a fixed surface in that case, and we're going to pick up a bold contribution in our formula. And we're picking up the contribution associated to the magnetic fluxes. And our result reproduces the one they had in that paper where they actually built the solution. Here we didn't need the solution itself. And that's also matching the large and limit of the topologically twisted index of ABGM. And they already noticed that they had like 2 branches of solutions, and here we interpret them as being related to the chirality of the spinor on the Riemann surface. So the next simplest thing we can do from this example is just to fiber the Riemann surface on the R2. And the effect of doing that is that now we have a non-trivial first Chern class. So we're going to pick up some additional contribution to our free energy that is related to the angular momentum of our black hole. And the effect on the field theory side would be that now the time direction is fibered over the Riemann surface for ABGM. And here as well, we expect to have these 2 branches of solutions. So now I just wanted to show another example where we don't have a fixed surface, but rather isolated fixed points. So we're going to replace the Riemann surface by a spindle. There are going to be many spindles took this week, so I won't say too much about it, but that's a weighted projective space that's basically pointy sphere with some orbifold singularities at the poles. And so now our killing vector is rotating both the R2 and the spindle. And so our fixed point set is composed by the 2 poles of the spindle. So now we're going to pick up 2 knots contribution. So 2 times like this knots term that we had in our fixed point formula. And this sigma is just a sign that is denoting the twist or anti-twist, which are ways to realize supersymmetry on the spindle. Twist is quite similar to the usual topological twist, and the anti-twist is a way that is proper to some spindle solutions. And by doing that, on the field theory side, you would be putting your ABGM now on S1 times spindle, The index for such a theory has been computed recently. I think maybe Dario is talking about it later. And our results match their prediction for this spindle index. I'm doing short on time. I'll say stuff in the discussion. So yeah, I showed you what the equivariant localization was and how to use it in particular for 4D supergravity with matter to obtain the free energy. Generically, you can also obtain other observables. We also worked out the fluxes with that and so on. And once you have this general formula I gave you, can just go ahead and pick a topology. Here we looked at these different kind of black hole solutions, but you could imagine picking some other prepotential, some other topology, and then you just have the free energy for free out of our general formula. So it's a quite cool result. But more in general, yeah, you can just use these equivariant localization methods in different setups. The parts that is kind of difficult is to build these equivalently closed forms using these Killing spinor equations. I mean, that's not difficult, but you get your hand dirty. But once you've done that, you have this general formula, you pick your topology, and you're done. But there are other interesting applications in supergravity. So, for example, we had this paper earlier this year where we were doing similar computations, but in the near horizon geometry of the black holes, worked in d equal 4 and 5 there, also with vector matter, but also with hypermultiplets. We're expecting to also be able to extend the previous result with hypers. And one application that is very interesting is to consider the full AGS times internal space solution as well. Then you can use this localization formula on the internal space and obtain then also some holographic observables, some free energy, central charge, fluxes of the holographic dual. We've done that with Chris in massive type 2A. And there is also this other approach of equivariant localization in supergravity that relies on some other kind of fixed point formula. That's the one I've shown you, and it would be interesting to see how these two approaches can be related. Some other interesting directions that should be pursued are to not use supersymmetry, because that's really not needed in equivariant localization. All that we need is asymmetry, and here we're taking this U1 that is associated with supersymmetry, but generically all you need is asymmetry. So it should be pretty straightforward to extend these methods to setups without supersymmetry. Another thing I've been putting under the carpets was that all of the integrals I was showing were even dimensionals. And actually, if you want to do equivariant localization on odd dimensional space, you would need slightly different fixed point formula than the one I've been showing, but they are in the math literature. Like, someone should go ahead and apply them in supergravity. That should work, just hasn't been done. And one thing that is also very promising would be to try to add higher derivative corrections to the supergravity action, and then you can, in the same way, build your equivalently closed forms and apply your fixed point formula. And by doing that, we should be able to match some subleading corrections in M on the field theory side, which you should also hear about later this week. So we're also expecting it to work. So thank you for your attention.
Questions? Can you bring one? Carlos is the nearest one.
Hello.
So, can you comment a bit about the non-SUSY situation? Why you expect it to work?
Because
Here you're using the RCS.
yes, but you need a killing vector, but it doesn't need to be the one dual to the R symmetry. Like here it's useful because then you have this relation with this bilinear and you use your Killing spinor equation, so you should find maybe some other ways to build your equivalently closed forms. But generically, if you just have this equivalent external derivative, d minus psi, psi can be any Killing vector of your solution. So it doesn't even need to be U1. But so it would just be like the same way we have this kind of form as the top form part. Here you would add like some additional terms, and just you would have to be like, that's just a technicality to be completing it into something that is closed. Thank you.
Thanks for the talk. I just wanted to figure out, can you tell me some more about how the theory is related to the free potential?
Oh, yeah, I could have had an additional slide with the relations, but that's really like some kind of derivative of this free potential, and like you take some imaginary part, some real parts, you compose the derivative. Like there are some very explicit formula for that. I think if you want to see them, there is either the Friedman book or like the Black Saddle paper. They have a super nice appendix summarizing this kind of theories. So, yeah, I don't have the formula in mind now. Like it's just you can express them with this object. Sorry.
I was just confused about these alpha factors that you have in front of the spin vector that you find in fraction. I was wondering, like, the final formula that you get the dependent GI in.
Oh, yes. Thank you.
Understand without any solution how the spin vector is acting on the model.
Yeah, thank you. So that's not the case for the bolt, but typically you're right that for the spindle we were still having like some weights there. And so typically you would be extremizing over these parameters. So that's something I didn't mention, but we're only posing like some subsets of the equations when we build our forms. And so typically you would get some results that are not directly on shell, but partially on shell, and you still have some parameters to extremize over, and these weights are typically these parameters you would still be extremizing over to get on-shell results.
Thank you very much for the talk. My question was just a little one because it connects with what we'll be talking about. So when you say that in a covariant localization, you just think the topology, do you mean topology or differentiable structure? Shall I repeat all of it?
No.
Okay. Maybe like mathematicians usually make this difference between topology and differentiable structure. I don't know if.
I'm not a mathematician.
Okay. Fair answer. Thank you.
No, sorry.
No
we keep referring to it as topology, and James is more of a mathematician, and he calls it topology, so I would think that's that, but I don't have a smartest answer to give.
So you mentioned the Black Saddle
On
story.
the side, who's the last person?
So you mentioned this Black Saddle story, and you mentioned the generalization with rotation that you did. Is that supersymmetry or extrema of both imposed? And did you like study the generalization like in detail, the actual solution?
No, that's actually the part that we're kind of proud about, is that we don't need to study the explicit solution. So
Right,
but yeah. Maybe, I think in that paper they did a bit of it, but I don't think they built it completely, but that would be there. But yeah, that's still supersymmetric and so on, but all our formalism relies on assuming that the solution would exist, but maybe it does not, but in case it does, then here is the free energy. That's kind of the philosophy.
A very short follow-up. What if multiple solutions exist with the same topology?
I mean, that's kind of what's happening here with these two branches of solutions, I guess. Okay?
Well, there are solutions with continuous parameters, so.
What do you mean by what spot? Like, should we be summing on them or these kind of things? Is that your...
Well, I mean, you've got one formula. You didn't find the solution. Which solution is it a formula for?
Yeah, that's a good question. I'm not sure I have anything smart to say about it. I'm sorry.
Okay.
I'll think about it.
Maybe one just quick comment or speculative comment about your. Can you hear? Yeah. I guess one expects that if there are continuous parameters, they wouldn't depend. The free energy would not depend on those. That's typically what we would expect. But there is much more to discuss, of course. I have one curiosity in the spindle slide.
Yeah.
Yeah. Why is there a question mark in the?
Because I sent my slide at 5 a.m. this morning and I
Sorry?
forgot to take out the
No, sorry, I didn't
comments.
understand the answer.
I forgot to take out the
Oh,
comments.
so, okay.
I hope no one would notice.
Okay. Okay. Good.
I wasn't
said
sure.
It was just a curiosity.
No,
nothing more
because
than-
these solutions have been built for minimal supergravity, and so with matter, I wasn't sure if there were also some stuff that were built or if that was completely new. So I wanted to look at the literature and solve that, and eventually the comments stayed there.
Okay. More questions? One there, up there.
So,
You had a comment about boundary terms that should not contribute to the final result of the action.
yeah.
Is it true in general, so or
No,
for
it's
specific
it's actually quite
solutions?
complicated to show. Maybe it's true in general, but the proof we've used here is very specific to the theory, and so you get some finite contributions that's going to cancel against like other things and so on. I mean, that's not a trivial analysis, and I don't think there is a straightforward argument. I mean, in minimal gauge supergravity, you can argue based on symmetries, but in the case with matter, we really had to go through the whole computations of these terms and show explicitly that they were vanishing, so I'm not sure how that generalizes for other terms.
Maybe one should have to assume like boundary conditions like ADS, asymptotic ADS, or in more general.
I think I'm not sure. I think it should be asymptotically or AGS, but I'm not sure about the assumptions anymore. Sorry, but I think so.
But the counter terms depend on what are the boundary conditions anyway. So you cannot ask this question before saying what are the ones. One last question, maybe? I guess we are done. So let's thank Alice again.